Okay, so what we're looking at is how we can solve equations that have trig functions in them. Now, if we have a look at this equation over here, root 2 times sine x equals 1, and we want to know the values of x, we could probably do this using our year 9 knowledge, where we just rearrange for sine x and then we take the inverse sine of whatever's on the right here, and there's our solution, and we give ourselves a pat on the back. But because we're aspiring specialists, we want to find every solution for this domain for x over here. Now, you guys have already graphed the sine function. If you were to graph it, you would know that across this domain, sine starts down here and it waves like this, where this is 2 pi, this is pi. Now, if we were trying to get a value out where sine x equals 1 over root 2, what we might discover is that this is y equals 1 over root 2. What we discover is that we're going to get an intersection here, and we're going to get an intersection here, which means that our value of x is both here and both here. And there's the problem. We have to find some way to not only find the first solution, which is going to be within that 0 to 90 degrees, or that 0 to pi on 2, we need to find that solution that's above pi on 2. Now, lucky for us, there's an automated way to do this. But we have to keep our unit circle in mind. First thing that we're going to do here is we're going to rearrange this equation such that its sine, or the trig function of the unknown, equals something on the right. So to do this, I first divide by root 2. So that's going to be 1 on root 2 sine x. And then, now what I need to do is I need to think about my unit circle. I might draw it off to the right here. When I'm looking at this value here, what I'm thinking is the sine of x gives me a positive value. The question is, where on the unit circle does sine give us a positive output? If I use my mnemonic, all stations to central, I know that I'm going to get positive values for sine in which two quadrants, Foreman? Quadrant
A and S.
Yeah, quadrant 1 and 2. So the mnemonic is all stations to central. The letter indicates which function is going to be positive. The first quadrant, all of them are positive. In the second quadrant, only sine is positive. For quadrants 3 and 4, only tan is positive here and only cosine is positive here. So what I'm expecting is my solution is going to be in quadrant 1 and quadrant 2. Now quadrant 1, we're looking at theta, which is this guy here, and that is the same as our non-right angled trig equation or trig questions, where we just do the inverse and boom, there's our answer. Now for the other ones, starting at the positive x direction, we're going to swing our angle all the way like this, and this is our theta here. Now if we tried to take the angle measurement over here, or of this one here, it's going to give us this interior angle here, not the exterior. I'm going to call the interior angle phi. Now if we think about it, from 0 to pi, how many degrees is that? Or how many radians is that? Pi. So if I wanted to know what my theta is over here, I'm going to go pi take away the phi. Does that make sense? So I'm taking I'm getting pi, and I'm taking that interior angle away to find what the exterior is. So we're going to get two solutions to this equation for one period. My first solution, well, firstly I'm going to write phi is going to be the inverse sine of 1 on root 2. And if we look this up in our reference table, which is on the back, it's the same as root 2 on 2, which is the same as pi on 4. So let's go. Our first solution is going to be x equals pi on 4 radians. Happy days. Second solution that we're expecting. We need to think. We're in the second quadrant. So our x is going to be our pi, take away our phi, which is pi on 4. That's going to give us 3 pi over 4. Therefore, x is going to be pi on 4, or it's going to be 3 pi's over 4. Does this make sense? Now let's verify it to make sure that that's correct. What we can do is, on our calculators, we can simply type it in, sine, actually we'll go pi on 4 into x, and then we can say sine of x gives us root 2 on 2, which is the same as 1 over root 2. Checking the other one, change it to 3 pi on 4 into x, sine of x gives us, lo and behold, root 2 over 2. Does this make sense? So step 1, arrange to make the trig function the subject of your equation. Sin x, cos x, tan x plus 2, whatever it is, make it the subject. Step 2, find the location of the expected output. Step 3, find your interior angle. The interior angle phi is always what you would get out of the first quadrant. And then step 4, find your solutions. And check domain. Seem okay? Do you want to practice one of similar complexity first, or do you want me to show you the hardest level of complexity? It's only one step higher. Harder, Matilda? Harder or another one? Harder, Foreman?
Alright, with that.
Do you mind if I rub this out for now? Okay. We'll go number 2. And yeah, so step 4, find the solutions to check for validity. All right, B. For B, we're going to go for
Bit late, mate.
yeah, bro.
I set mine on for 9 instead of 8 by accident.
You walked through my frame.
Oh no. Sorry.
It's okay. I'll edit it. All right. So we're going to go minus 2 cos x equals root 3. For the values of x can be minus pi all the way up to 3 pi. A little bit tricky. Now, first step, what should we always do, Zoe? Rearrange to make what? Yeah, we always want to rearrange to make a trig function a subject. So this is going to be minus root 3 on 2 equals cosine of x. Bingo. Now, next step. I draw a little picture because a picture paints 1,000 words. The question I ask is, where are my solutions expected? How can I ask a more specific question? Where is cosine going to give me negative values? All stations to central. Cosine is positive in quadrants 1 and 4. Where is cosine negative? 2 and 3. So therefore, we are expecting solutions here, and we are expecting solutions here. To be able to work out the solutions here, we know that our theta is going to be pi take away the interior angle phi. But what about down here? The angle of interest theta starts at the positive x direction or x-axis and swings all the way around to here. It's going to be made up of the interior angle plus pi. So theta in this case is going to be pi plus theta. Now the other question we have to ask is what is phi going to be in this instance? Remembering that phi is the would-be angle. Any ideas how we'd calculate phi? Think back to complex numbers. Do you guys remember when we were trying to calculate the argument in complex numbers, we pretended the imaginary and the real part were both positive? We do the same here. We just pretend. This gives us the would-be interior angle for quadrant 1, which allows us to discover the actual result for here and here in quadrants 2 and 3. So the inverse cosine of root 3 on 2 is going to be pi on 3 radians. No, pi on 6 radians. Is that correct? All right, next part. This is where it gets a little bit tricky. We need to start solving for our solutions. Our first solution is going to be this quadrant over here. So x is going to be pi minus pi on 6, which is going to give us 5 pi's over 6. Is that within our domain? Is it less than 3 pi? And still more than pi, so that's okay. For our second solution, we're going to get x equals pi plus pi on 6. So that means we're going to get 5 pi's over 6. Not that. We're going to get 7 pi's over 6. Is that solution okay? Yep, that one works. But there's a problem here. Think about our domain. Sine of 2 pi, so sine over a domain of 2 pi looks like that. But we're going, oh sorry, that's sine. We need cosine. Let's try again. Cosine over 2 pi looks like that, doesn't it? But we're starting it a little bit earlier. We're starting it at negative pi. So that means we're doing that. And that means that this is going to go all the way up to 3 pi. Excuse the grossness of my drawing. Yeah, I think that's it. So what we've found is that we found a solution here, and we've found one there. How many more solutions are we going to get here? 2 more. We're going to get one here and one here. The question is, how do we find where they are? The simple answer is you use your calculator. To algebraically show that you're looking for them, you go plus 2k pi here, plus 2k pi here, where k is just some integer. The value of k isn't determined just yet. So at this point, after setting this up, we use our calculators. You can do it algebraically, but I don't think it's a very sensible thing to do. And to be honest, I wouldn't like giving this as a question because you're testing someone's fraction ability, not their solving ability. So what you can do is we clear this. We set a variable k, and we start it off at 0. Next, we pump in our first equation. It's going to be 5 pi's over 6 plus 2k, where are we? Pi. First answer, that's cool. Now, if we want to get another answer, we ask ourselves, are we expecting the next answer to be less than 5 or 5 pi on 6 or more than 5 pi on 6? If we look at our graph, we're expecting it to be more. So figuring this out, we change it to 1 And then you end up getting 17 pi on 6. Is 17 pi on 6 less than 3? 6 3s are 18. So yes. So the first answer is going to be 5 pi on 6. The second answer is going to be 7 pi on 6, as we expected. The third one's going to be 17 pi's on 6. And then to find the final solution, we simply put in the 7 pi over 6 plus 2k pi. And booyah. Is this is this solution valid? No, it's too high, so we take it up, we change the k to -1, we go down, bam, minus 5 pi on 6. My drawing was wrong, but that's okay. Do you see how you can use technology to solve these? All right, the quicker way to do this that you can use to verify, you can't do it to solve, you can do it to verify because you're going to get asked to do that analytically. The quicker way to do this is you go options, calc, solve n for multiple solutions, minus 2 cos x equals root 3. Solve for x, please. Go. Multiple solutions exist, indeed. However, you scroll across and you find the ones that are within your domain. That can be used to verify. Alternatively, you can do the analytical work as shown over here, and then just throw it in, over here, here and here, and then throw it in the calculator like that. Does that make sense, guys? It's quite a lot, isn't it?